Hello everybody, and welcome back to another Universe Sandbox video. Now, as you saw in the title and thumbnail, we're going to be talking about interstellar travel and how it's cheaper than you might expect. Now, to start off with, we need to first ground ourselves in this system. We obviously know here's the sun, here are all the planets going around, but how much delta V does it actually take to get to each one? So, we're going to go ahead and head over here to Earth, and we're going to do a bit of Kerbal Space Program in Universe Sandbox here. We're going to go ahead and grab, the Parker Solar Probe, because that's the most fitting for this. We'll go ahead and put that into an orbit, and let's say we want to go to Venus, because the Parker Solar Probe did actually go to Venus. We can talk about that a bit later, so we want to wait for a Venus window. Venus window is about 45 degrees behind us, I believe. Kind of guesstimating here. But yeah, we're going to wait for Venus to get right about behind us there. So there we are. There's Venus, and we're going to go ahead and head towards Venus. So we want to wait for the Parker Solar Probe to be in the right spot. Right about there actually seems good. And right now, currently in low Earth orbit, the Parker Solar Probe is doing about 7.31 kilometers per second, which is standard for a low Earth orbit, although we might be a little bit higher. It's fine. It doesn't really matter for this case. It's low enough. So anyways, we're going to go ahead and start accelerating. And we don't need to accelerate by a bunch. So as you see, we accelerated about 1 kilometer, 2 kilometers, 3 kilometers, and we've practically left the system. And it's kind of freaking out a little bit, because it doesn't know what to do. So we're just going to go ahead and leave the Earth's sphere of influence. So as Parker Solar Probe leaves... Oh, that was the wrong way. We're going to Mars. But if we actually make sure that we're heading the right way, as you can see, once we leave the Earth's sphere of influence, we will end up on a trajectory that perfectly matches Venus's orbit, perfectly lines up, and as everybody who's played Kerbal Space Program knows, it'll take a bit of time for us to get to Venus, but eventually we will catch up with Venus, and if I had any way of precisely maneuvering this thing, we would have got a Venus encounter. But yeah, as you saw, only 3 kilometers per second on top of our orbital budget, which is super cheap. Not even really that much more than getting to the moon. If you can get to the moon, you can usually go interplanetary. Because, yeah, it's not that much more than lunar delta V. However, if we want to go to Jupiter a bit further away, that's going to require a bit more delta V. So let's go ahead and do that. So we'll go ahead and throw in another Parker Solar Probe. Thing is, I don't actually know how much delta V getting to Jupiter requires. I'm going to guess it's about double. So instead of going like 3, let's go basically like 13. Should be good enough. Let's see how far that gets us. Alrighty, not quite. So we need to accelerate by another kilometer. Pretty much. But as you can see, that gets us over to Jupiter. And if I time this right, we might get a Jupiter encounter. No, we were a bit soon. Come on, Jupiter, catch me! Ah, no, we were a little soon. We just missed Jupiter. But as you can see, these transfers to other planets are really not that much more than the delta V required to get into low Earth orbit. Just half or double velocity is all you need in order to reach some of the solar system's most famous destinations. However, this is only possible because the Earth itself is moving. As we take a look at the Earth, we can see that it's moving at around 30 kilometers a second. So whatever speed we have leaving the Earth gets added, in the case of going to Jupiter, or subtracted in the case of going to Venus. So if we leave Earth with an excess of 3 kilometers per second, that gets subtracted, and if we look at this, at its apogee, it's going about 27 kilometers per second. So, getting to other planets in the solar system is easy. Getting to the sun, on the other hand, is where it gets hard. Let's say we wanted to send something from Earth into the sun. We're just going to send Earth into the sun because it's easier than putting a probe around it. So as you know, Earth is going about 30 kilometers per second. So in order to send something into that sun, we need to reduce its speed by 30 kilometers per second. So as you can see, as we reduce the speed, we go down, we're about Venus height, then we get down to about 23, then we're like at Mercury's height, and then we keep going, until we're practically at 0. Now, one of the reasons why it takes so much delta V to go down into the sun is because as we reduce our speed up here, we are losing kinetic energy, but because we're so high up, we're gaining potential energy. So as we fall towards the sun, our potential energy turns into kinetic energy, blasting us away from it. So as you can see, we didn't quite reduce all our speed, and once we get down over here to the sun, instead of going about 30 kilometers per second, we instead accelerated the Earth to 123 kilometers per second, which is that many miles per hour. It was very quick. Very, very stinking quick. Because as you get closer to the sun, its gravitational effect on you gets stronger. Mercury is booking it at a whopping 43 kilometers per second, Venus 34.9, and if we were to put Earth into a stable orbit at this height, it would have to be going a whopping 91 kilometers per second. And also, yeah, I feel like this close to the sun, most life probably wouldn't survive. Just taking a look at Africa over here, and they say the sun's bigger in Africa, but I don't think it's quite that big, if you know what I mean. But yeah, what this all boils down to is, even at 4 kilometers per second, it still won't crash into the sun. Have to get that pretty much all the way down to 0. And I mean that'll crash into the sun. Or not? I mean, it kinda did. The oceans are gone. Okay, that's what I noticed first. And it's probably very warm. Ah, yes, definitely very warm. Very warm. But the fact that it's still here is surprising. And I mean, Australia's still here. Look at that, Australia's still there. I mean, this is a typical day in Australia, really. But yeah, as you saw, lots of delta V to get that to crash into the sun. But if you go out to, let's say, Jupiter, it's actually going to require less delta V to get to the sun, because Jupiter, all the way out here, is actually only going a mere 12.5 kilometers. So less than half the speed that Earth was going. So yeah, in order to get Jupiter to crash into the sun, really, really cheap, bam. There you go. Jupiter's heading into the sun now. I'm just going to speed up time a little bit. Let Earth do its fun little dance as it gets incinerated. Sorry, Earth. Look, Jupiter's here now, though. But Jupiter's here. Look, Jupiter's here. And glorp. And yeah, let's just go ahead and end Earth's misery. There. No speed for you. Goodbye, Earth. And now you're in the sun. Sklorp. Alrighty. Now, the long and short of it is, the closer you are to the sun, the harder it is to get to the sun. Counterintuitive, but it makes sense when you think about it in terms of potential and kinetic energy. The closer you are to the sun, the faster you're going, meaning the more kinetic energy in order to eventually jive into it. However, no matter where you are in the solar system, it's always going to take less delta V to leave. No matter if you're at Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, or Neptune. It's always going to take less delta V to leave. For example, if we go to Neptune, it's only going 5 kilometers per second. However, if we just give it just a couple more kilometers per second, as you can see, we are making our way out of the solar system. Actually, if we go to like 8 kilometers per second, that's kind of our escape trajectory. There you go. But that's still less than double. That's still less than the delta V it would require if we spun this the other way to get to the sun. Again, pretty much the same is true with all these planets. And now, just to prove my point, I've gone to the liberty of taking all the velocities of all the main planets, you're safe, Pluto, because you're not a planet, doubling it, and then subtracting 1. So each of these planets are going double minus 1 at their velocity. Meaning that if I applied this speed in the opposite direction, so instead of using it to leave the solar system, if we were to instead use it to crash into the sun, it wouldn't be enough. And just to prove my point, here is all the velocities in the opposite direction, and as you can see, Mercury missed the sun, Venus missed the sun, Earth missed the sun, Mars coming to join the party, and it also missed the sun. I think Mercury got thrown into the sun through gravitational influences. That's not my fault. Venus is dead too. It's gravity, and here comes Jupiter to mess with gravity some more. Yeah, when the gas giants get here, I feel like Earth and Mars are gonna go, because, I can't control the fact that they have gravitational influences. Because, yeah, here's that, yeah. But as you can see, not crashing into the sun. Not crashing into the sun. Actually, Mars and Earth might be fine. Yeah, they're cool. Oh, Mars has found a new orbit. Mars has found a new, very spicy orbit. I think it's a little warmer now. Ah, but too warm. Ah, shoot. I think I might have overdone it a bit with the terraforming. But yeah, if I go ahead and play this out, and speed this up, because space takes a while, we can see, pew, Mercury shot off, pew, there goes Venus, Earth, Jupiter, Mars, Uranus, Neptune. They're all flying away. They're not coming back. All I did was double their speed, minus 1 kilometer per second, just because it's less than the speed it requires to crash into the sun. They're all gone in less delta V than it would take to crash them into the sun. Now, I bet you're wondering where I'm going to with all this. Well, we're trying to get to the point where we figure out if this is enough speed to get to another star. And the closest star to us is Alpha Centauri. So what I'm going to go ahead and do is I'm going to go and set up a mock Milky Way galaxy. We're going to go ahead and grab a black hole, Sagittarius A star. Now, we're going to go ahead and put the sun a lot of light years away. I don't know exactly how many light years. It's quite a few. Let's just, yeah, 250 light years. And then we'll put Alpha Centauri about 4 light years away from the sun. There we go, but still in orbit of Sagittarius A. So we have a very dumbed down Milky Way with just our 2 stars in orbit of Centauri. So let's go ahead and add our planets to the sun. Add planets, there we go. Now we have our solar system. If we want to get Earth, or a probe to Alpha Centauri. So if we wanted to go interstellar, we wanted to get to Alpha Centauri, how much delta V do you think that would take? Again, we're kind of in an orbit, so we could do a basic Hohmann transfer, although you'd be spending a very long time doing a Hohmann transfer, and that's not usually how we plan to go interstellar. We usually plan to go interstellar with a brachistochrone trajectory, which means we head straight there. We burn straight there. So, if we line up so that the Earth is probably about here, go ahead and get Earth there, and now we're going to go ahead and double its speed. So, we'll go from about 30 kilometers to 60. And again, that's probably in the wrong direction. But let's not do that. Let's wait for the Earth to be around here. I think this is a good spot. Oh, and it's... some weird stuff's happening to Earth. I don't really know what's going on. Either way, though, we're now going to Centauri. And we'll see if we hit it. So yeah, we're aiming kind of where it should be. And we're going to go and see what happens. So, goodbye. Leaving the solar system, going interstellar. Can we hit Alpha Centauri with less delta V, or about the same delta V as it would take to hit the thing? The other thing. Where's the Earth? I misplaced Earth. Does anybody know where Earth is? I lost it. Oh, I see fragments. I'm slightly worrying. Let's try that again. Let's try going to Alpha. Let's send Mars this time. You know, Mars is probably better off at going. Yeah, Mars is probably better suited for this. Okay, hi Mars. Let's go ahead and double your speed. Alrighty, Mars is going interstellar. Let's go Mars. Spaceship Mars. Will Mars make it to Centauri? 4 light years away. I mean, yeah, we're making it. We're going about 100 years a second, so it's definitely not a quick journey. Definitely not a fast journey. But we are making it to Centauri. We just missed it. So if we had a way of aiming, you can get to Centauri for less delta V than it requires to get to the sun. Would you look at that? I mean, obviously, if you wanted to stay here, but I mean, if we're just comparing sun dive to Centauri dive, I think it's pretty clear. Centauri dive is cheaper. Obviously, sun dive is easier, because all you have to do is just reduce your speed, but, like, I mean, pretty much any of these planets, if we just double their velocity, maybe reduce it by a little bit, so that way we don't go too quick. I mean, Jupiter's gonna miss it, probably. We need a faster planet. I know. Venus. We need a faster planet. Okay, Venus. Oh no, Venus is gone. You know what? Let's go Pluto. I know Pluto's not that quick. Oh my goodness, we're going like mega years a second. Okay, I know Pluto's not that quick, but if we launch it right about there, bam, that might hit it. Ooh, we're going way north though. Your inclined orbit's really not doing any favors for you there, buddy. Speed Y. Let's zero that. You know, we don't want any vertical. There we go. Go get him, Pluto. Go get him. Pluto's a very common dog name, so I think it's fitting. Go fetch. Go fetch the other star system. Maybe you'll be treated as equal there. Come on, come on, come on, come on, come on, come on. Ah, it's so close. So close. So close. We keep missing. How can we keep missing? We're firing all the ammunition we got. How do we keep missing? Saturn, your turn. Go. Oh, is Saturn gonna hit it? Saturn, go do it, Saturn. No, Saturn missed too. We're just not great at aiming. Oh, we passed its orbit though. Alrighty, the final 2 ones. Uranus and Neptune. Go get him. I think Neptune's closer. Uranus is going the complete wrong way. Neptune. Oh, Neptune. Oh, Neptune. I'm gonna cheat a little bit. We're gonna do a little bit of braking. I mean, if this is a spaceship, is what you could do, right? You could do a bit of braking, you could do a bit of accelerating. We're treating this like a spaceship now. Go. Go. Get it. Get it. Yes. Okay. Correction. Nope. Catch it. And break it. Break. The rendezvous. How does one rendezvous? There we go. Hi, have we rendezvoused? Have we successfully rendezvoused? If I reduce my speed now, do we get orbit? Or are we not close enough for that? Hi, how are you? Okay. Well, there we go. Yay, we're in orbit. We captured into orbit around Alpha Centauri. Yay. We went interstellar. But yeah, there you go. So it is cheaper to go to another star system than it is to crash into your own sun. I mean, I'm pretty sure that wraps up the video. Yeah, that was quite fun to figure out. I actually didn't know what the answer was going to be at the start of this, but as I started putting the pieces together, doing all the bits, like, it just dawned on me, like, oh yeah, this is so much cheaper. And again, this is also, like, comparing it to stuff like the Parker Solar Probe, which used a bunch of flybys of Venus to bring it close to the sun. If you think about it, if instead of using all these flybys to Venus to get close to the sun, if you instead use them to eject yourself from the solar system, it would kind of be the similar deal. Similar to the Voyager probes, which are currently on their way out of the solar system. If they were aimed at a star or something, they would make it there in roughly the same amount of time that our Neptune made it there, because they are going at right about the same speed. So anyways, if you guys enjoyed this video, please be sure to leave a like, subscribe for new videos, have a great rest of your day. And yeah, let me know if there's anything you want to see. Obviously, we're going to do how the solar system moves next, because that was on my poll. But after that, I'm open for ideas. I know I want to do like a Terraforming Mars video at some point. But other than that, it's open. What do you want to see? What do you want to hear? What do you want me to debunk? Space myths. Maybe we'll do that. Space Mythbusters. Ooh, that could be fun. See you guys later. Bye!